Right. So we're supposed to start a new topic that is not only applicable to probabilistic graphical models, but to any sort of Bayesian inference, and that is what is called variational methods to approximate posterior distributions. Okay, and we will do some elementary examples today. Maybe some apply to probabilistic graphical models, and there is a lot on this topic, so maybe we will spend another 2 lectures or 3 lectures, depending how exhausted you seem to be, in the days ahead. So try not to sleep, okay? All right. I believe Shuvik sent you the notes, but I will post them. If you find any mistakes on these notes, please email me. All right. So we're going back to the standard problem where we have some observed data that I denote here with X. Z are the latent variables, and we want to compute the posterior of the latent variables given the data. The light came on, and it seems the camera, I'm assuming it should be working.
Yeah, it's working.
Okay, it was not exactly when it's supposed to be. It was dead. So.
And then it just
miracle of nature, Notre Dame miracle. Yes.
Thank you.
All right, thank you guys. So the probability of Z of X, Bayes' rule basically is given like that. So most of the machine learning subject area is to compute this posterior, okay? Now, in addition to Z, you may have other parameters the way we have seen up to now, and we will do some examples, but let's concentrate on Z. All right, so we are assuming that this posterior is not very easy to compute, or it's not maybe even given in any analytical form. Maybe it's a computer code, and somehow we're going to try today to discuss methodologies where we can have some approximations of the posterior that they are explicit in nature. So you can think, taking a general posterior and approximating it as a Gaussian. I mean, that can be a simple example. Maybe a Gaussian will not be enough. And it would not be enough because maybe Z is very high dimensional. So you can think this in the examples we did with graphs. Z can involve many variables, so approximating the joint distribution of Z as a Gaussian maybe is not a good idea. All right. So there are 2 methods of doing this, and so one is basically to approximate the posterior with samples. And in some sense, we discussed this a little bit in the context of the previous lecture when I referred to particle methods basically to compute the predictive and the smoothing distribution in state space models. So this is using Monte Carlo effectively, right? And the method that we're going to discuss today is basically it's a deterministic method in many ways, and falls in this category of what we call variational inference. So we're going to try to approximate the posterior with some form that is sort of computationally easy to work with, and that form is going to involve a factorization, so an approximation that factorizes this in distributions over each of the variables in Z. So let's say if Z is 3 variables, we're going to approximate this as Q1 of Z1 and Q2 of Z2 times Q3 of Z3, and then try to approximate each of these Qi distributions. We will see that this actually leads to methodologies already known in statistical mechanics for centuries basically. So in many ways these methods are coming directly from physics, okay? And sort of the techniques that they applied from simple inference problems to probabilistic graphical models to deep learning to everything. So they're very powerful methods, but they're approximate methods. Approximate methods is you get what you approximate it with, right? So if you're not happy with it, too bad. Okay? So in some sense, this is a good active area of research if you want to come up with something better, following basically the ideas of variational inference. All right, so let's introduce some of the basic of the problems. So we assume we have collected some data, x1 to xn. We are assuming that we have latent variables z1 to zn. So you notice here the number of latent variables is the same as the number of data. So you can think of a problem where, if you are talking, let's say, about a Gaussian mixture, for each x there is a z that tells you from what component of the mixture this is coming. So we have n data points and n latent parameters, but later on we can enrich this with static parameters theta. But right now this is what we have. This is our joint distribution. We have played with it when we worked with the EM algorithm, and we want to approximate the posterior and also the model evidence. Okay? So we're going to denote the approximation as Q of Z. So this is the exact posterior, and this is the approximation of that posterior we're going to try to compute. We don't use usually in the notation Q of Z given X, right? So this is a distribution in Z, but remember it's an approximation of a posterior distribution. Okay, the very fundamental equation that I have to use today, and you need to remember it because it's essential everywhere in machine learning, is the equation that you see there, that it says the log of the evidence. So this is the likelihood of the data. So the log of the likelihood of the data is this lower bound, which I will define shortly, that's only a function of Q, plus the Kullback-Leibler distance between Q and P. So P is the exact posterior, Q is the approximation we try to model. You may say, why is this useful? Well, you will see shortly why is this useful. Okay, so let me define things. The lower bound is defined basically as the expectation with respect to the distribution Q of the log of the joint likelihood divided by Q of Z. So this is the lower bound. You may say, why do I call it a lower bound? We will see that shortly. And the KL distance between Q and P is defined this way. So you may want to memorize one of the two definitions with a sign so that you do this properly, right? So if you put a minus sign, and this is the distance between Q and P, Q will come there, and this will be the exact distribution you try to approximate. If you want to put the sign inside and get rid of it, basically you're going to have to reverse the order, and you have Q of Z divided by P of Z of X. Okay. Everybody familiar with the KL distance of distributions? Okay, it's not a real distance. Okay, it is a non-symmetric quantity. We will see actually today that if you have the distance between P and Q is not equal to this. So this is very important, that this is the distance of Q from P, not of P from Q. Okay, this distance is 0 when Q and P are equal. It is greater or equal to 0. And because it's greater or equal to 0, what you see here is greater or equal to LQ, and that's why we call LQ the lower bound to the log likelihood. You see that? because the KL distance is positive, right? So the L of Q is a lower bound basically to the log likelihood. So if you want really an approximation of the log likelihood, because this is computationally difficult thing to do, what is very easy to do is compute L of Q, because it involves the joint log likelihood here, okay? And we already have seen in the context of expectation maximization that there is a reason you would like to work with P of X and Z, because, for example, if this joint distribution is Gaussian, everything falls nicely and the calculations is easy, but working directly with this, it requires integration in Z, and that's not convenient to do. Okay, so let's prove this equation. The proof is trivial. So we use the definition of L of Q. So L of Q, we define it to be like that. So this is what it is. So I'm expanding, so Q of Z log of P of Z of X plus Q of Z log of P of X minus Q of Z log of Q of Z. All right, nice. Okay. Now, log of P of X does not depend on Z, so I can put outside the integral, and I'm assuming Q of the distribution Q is normalized, so the integral of Q dz will give me 1. So what I'm going to get is, from this term I'm going to get the log likelihood, and then I have basically the rest of the terms, which is Q log of P of Z X, okay? This term comes from here, and then minus Q log of Q is there. So this is minus the Kullback-Leibler distance. This is the log of the evidence. So you can see that the log of the evidence is the lower bound plus the KL distance of Q and P. Okay? Very simple derivation. It is extremely fundamental. So if your head is spinning and you say too many equations, you know, well, you know, this is, you will see it actually in publications. This thing's used with zero explanation because you're supposed to know it, okay? So you don't explain things that you're supposed to know. All right, so we explain why this is the lower bound, okay? And this is the picture sort of you want to remember. The only thing we have when we have data is this evidence. So we're always trying to maximize the evidence of the data. So whatever unknown parameters we have, such as Z or static parameters theta, the only really way we can, in a Bayesian setting, we can compute the unknowns is by maximizing the evidence, okay? And we just have seen that the evidence has two terms, the KL distance between Q and P and the lower bound. So you can think the problem in two ways. One is you say, I'm going to maximize the lower bound, all right? If you maximize the lower bound and to make it equal to that, basically you minimize the KL distance, you bring it to 0, or you can directly work with the KL distance. So whatever is computationally tractable would be the way to go. But as we will see, only for trivial toy problems we work with the KL distance. The lower bound is what we have to play with. All right. In the literature, depending what book you read, you know, to what community you discuss things with, the terminology for the lower bound has different physical meanings. So I'm going to give you one of them in the context of physics. So we said the objective is to maximize the lower bound. You can think of this as minimizing minus the lower bound. So if you calculate minus the lower bound, by definition you plug in a minus there, then you get minus Q log of Q. That's the entropy of the distribution Q. And then you have minus Q log of P of X and Z. And the second term here, all right, you can write it as the expectation with respect to Q of an energy function that I define here to be minus the log of the joint log likelihood, the joint likelihood of X and Z. So this E here is minus ln of P of X and Z, okay? So basically what you have here is you have this average energy minus this entropy, and this is basically what people in physics call the Helmholtz free energy. All right, so the problem really of computing Q is the same as minimizing the Helmholtz free energy. Okay, and actually, you can play around with the definition of the energy, and you can bring the problem to a form of minimizing other sort of energies like the Gibbs energy and the like. Okay, so you can immediately see the similarities with statistical mechanics. All right, I have another interpretation. We don't really need it, so rather elementary. Okay, so we go to the real problem now. We have a distribution, a posterior of z given x, and we want to approximate it with q of z. So z is high dimensional, so we have lots of z's. And let's not worry about parameters. Well, actually, these are not static parameters. So the way it is written here, it says, if you approximate this, let's say, to be a Gaussian, and omega is the mean and the variance of the Gaussian, then effectively, you can think of the problem of computing these parameters omega that define this distribution. Okay? That's not what I wanted to do, but there is an example basically that demonstrates this before we go to the general methodology. So let me show to you this sort of, it's really not a variational method, but it demonstrates what exactly we're going to be doing in a general context. So think that you have a distribution that is not very easy to work with. So there is an exponential there, like a Gaussian, but there is a sigmoid function, and the distribution, I suppose, is this one. Okay, it looks like that. And you say, I want to approximate this with a Gaussian. Okay? Now, an obvious way to approximate this with a Gaussian is using the Laplace approximation. Can somebody remind me what's the Laplace approximation? I know maybe we haven't used it too much in this class, but we used it last fall, and it is standard in machine learning. So, and maybe you can guess from the picture what the Laplace approximation is. So what's the Laplace approximation? Okay, but eventually it's a Gaussian with what mean? Where is that Gaussian center? Huh? It's centered on the zero or on the mean of the actual distribution? On the mean, okay. I mean, it looks to be zero here, and the covariance is defined using what? The curvature of the actual distribution that you see here on the mean. Okay. So basically what you do is, yes, you do a Taylor series expansion, you approximate the mean and the second order term, and effectively you get a Gaussian center around the mean with the correct curvature that matches, the curvature defined by the covariance. I'm sorry, the curvature of the covariance defined by the curvature of the distribution you want to approximate. Now, here what you see is, and we will be discussing these ideas today, is actually a variational approximation where in an elementary way, because this is a distribution in a single variable z, you can pose the variational approximation as one that minimizes the distance between q and p, where if you take q to be a Gaussian. So you want the approximate distribution to be a Gaussian, and you say, what is the Gaussian that minimizes the KL distance? And notice how big difference you get from the Laplace approximation. Significant difference. Okay? So not only basically there's a difference in the peak of the distribution, but also you can see the support of the distribution is very much different from the support of the Laplace approximation. But both are Gaussians. Okay? So Laplace approximation, and here is the variational approximation. And this, I think, the plot on the right shows what is that, the curvature. Okay, So this is, I think, is just the curvature of the two distributions, basically showing if this is the Laplace approximation, you notice it matches basically the curvature of the exact distribution, okay? And this is the variational. I'm so bad with colors, you know, so I need to, okay, so this is the variational approximation. Again, this is a trivial problem, right? It gives you a sense of what the variational methods will do, and in this case, there's no point of forming the lower bound because we only have one variable, basically, and there's no need to go to beyond the minimization of the Kullbaum distance between Q and P. All right. So I started saying this without realizing that it was a few slides down. Let's take the real problem now and say that Z is high dimensional. So we need to approximate this. So the first thing we do in these variational methods, we factorize the distribution Q of Z as a product of the distributions of QIs of each of the Z's. So if you think of this, you know, if you have two variables, Q1 of Z1, Q2 of Z2, okay? So if somehow you approximate each of them to be a Gaussian, you're going to have a product of Gaussians in each variable, all right? But it's a factorized product, okay? So this is the essential part to start with, all right? So we're going to use this limitation, this approximation on defining Q of Z, and then somehow we're going to use the maximization of the lower bound to try to compute what is the form of these QIs. And we're not going to assume that they are Gaussian or anything like that to start with, so we will do this as general as possible. And after that, we will see exactly with applications on if we need any additional approximations. So I can tell you again, this is nothing new in machine learning. The machine learning people basically stole the idea from statistical mechanics, and the derivation we will do basically leads to the classical mean field theory from quantum mechanics. Okay, so there's nothing new. And actually, that's why a number of very smart machine learning people, especially in Europe, actually they used to be former physicists who switched to machine learning so they can make some money. Okay? And they are very successful because their intuition pays off. All right? If you work just with equations, you're missing reality, and these people know what reality is, and they have done some significant advances in this area. Okay. All right, so this is our factorization. All right, so we plug in this to our lower bound, and remember the lower bound, it was an expectation with respect to Q. There is Q, and inside here we have the log of the joint likelihood divided by Q, which Q was this product of all of this, and because I have a log, the product, this product here becomes summations of the logs. Okay? You see that? Again, the actual lower bound here, Q, log of P of X, comma Z, divided by Q of Z. Q of Z is that, so you have log of that, so you get summation of the logs. Okay. Since we have a factorized form, what we're going to try to do is we're going to try to approximate each term in the factorization one at a time, right? So to see if if that is possible. And again, for those who have a physical intuition and have taken a course in statistical mechanics or in quantum mechanics, this problem is going to be sort of solved to self-consistency. And what that means is we're going to compute each of the factors, let's say the factor Qj, while keeping the rest of the factors to some values. And then we will then update the next factor, keeping the rest constant. until effectively, as we iterate through the factors, no further updates are needed. This is what's called self-consistency, the way we solve basically the Schrödinger equations. Okay, so I'm going to isolate the factor Qj. So we're going to compute, we're going to try to maximize this lower bound with respect to Qj. Okay, that's our objective. So follow the algebra because, it's blurry from my direction here. So we want on this thing to have only Qj. So let's look at this term. What I have done here is there is a product of all the Qi's. So what I did is I put this product inside the integral where I include all the terms but j, and then I do the integration of j separately. Nothing fancy. You see that? Right? I had an integration in all the z's, but now I integrate in all the z's but j, and then the integration of j separately. So this term, you get it like that, right? Is basically the average of the joint log likelihood with respect to the distribution of all the other variables but j. Okay? All right. Where is this thing coming? So I have, so I'm looking on this term on everything except j. All right? Everything except j. And will you agree with me that here I'm only going to have the product of the Qi's, all but the term j, because the term j will be integrated with zj and will give me 1. Because there's no j there, zj. Okay? And then I'm going to have an extra term where I pick up here the log of qj, and I'm going to keep here the log of the qj term as well. All the other qi terms will be integrated to 1 at a time, because the q's are normalized. Okay? All right? So I am, let me call this whole thing, this whole parenthesis, because it's going to be a function of zj, because all the other z's will be integrated out, right? So I'm going to call this p with a curl of x comma zj, okay? And I'm calling this log of this, the whole integral, okay? We will see why. It doesn't matter right now, just I define this to be log of p curl. All right, so this is qj times that. Okay, and remember, I only want to keep the terms in zj because I want to do a maximization with respect to qj. Okay, so the only thing that I don't see any qj here. Do you see any qj on the second term? There is nothing there, so we don't really care. We call it constant. And then we have the entropy basically of zj, which is this. Okay? The rest is basically functional optimization, and that's why these methods are called variational. You're going to have to take derivatives of this with respect to qj, all right? And set this equal to 0. But, you know, we can immediately see also from, this is the lower bound, right? We can see that without any calculations, actually without any derivatives, that this thing here is minus the Kullback-Leibler distance of qj from this p curve. Do you see that? You remember the Kullback-Leibler distance without the minus sign here, right? It will be a minus integral of qj log of this divided by qj. So you're going to get, there was a minus, and this is in the denominator, another minus gets plus, and with this thing we get here minus, which is this, plus that term. Okay? So, immediately you can see what's the optimal solution that maximize, what is the qj that maximizes the lower bound L of q? Where we assume again, we do the optimization one term at a time, that the rest of the terms are happy being left alone. Okay? So what is the optimal QJ? We want to maximize this. With the minus sign, we want to minimize the KL distance. What's the minimum of the KL distance? You haven't had lunch because I haven't. Huh? 0, thank you. All right. 0, that's the minimum. And when is the minimum happening? For what values of QJ? When QJ is becoming equal to what? Peak curl. And so, all right. So QJ will become equal to this. Okay? And, all right. And let me just write down, so we define this to be this peak curve, log of peak curve, right? So what I'm writing here, log of peak curve is, this is my definition, right? This is what I had. So will you agree with me that the log of peak curve is the expectation with respect to all the distributions except J of the joint log likelihood? You see this, right? It's an expectation with respect to all the Q's but J, all right? This is the expectation of, with respect to all the Qi's but J, okay? And you told me that Qj is optimal when it becomes equal to P curl, all right? Come on, I'm looking for that equation, okay? So what did you tell me? That this is optimal when this becomes equal to that. So, which means if I take logs, the log of Qj is equal to log of P curve, and log of P curve was this, all right? And if I write this, if I normalize it, this is the optimal distribution Qj, okay? Look at it very carefully, okay? All right? Usually an easier way to remember is this equation here, okay? Rather than this. So the log of Qj is the average with respect to all the other z's of the log of joint log likelihood. Okay? Now, obviously, if you take an average with respect to all the other q's, right, you will have to iterate this. That's why I said you have to run this to self-consistency. So you start, let's say, and you approximate, you find the optimal for Q1, keeping all the other Q's fixed. Then you go to optimal of Q2, keeping Q1 and the rest all fixed. And you keep iterating until basically you're happy that there are no changes. That's what self-consistency means. And now, why do they call this the mean field approximation? What is about it that makes this to sort of be a mean field? Mean field. I mean, what, you can extrapolate from the words. What is mean? Mean field. Expectation, right? So to calculate this, right, you're using the expectation of the log likelihood, of the joint log likelihood, where you average with respect to all the other distributions. So this is sort of, if you say I have many electrons moving around and you want to write an equation for one electron, you're doing the computation in the average field of all the other electrons. And then you get a one particle sort of equation. In this case, we get an equation for the distribution Qj in the average distribution of all the other ZIs, all right, in our factorized distribution. All right? So that's where the mean field approximation, so you can think, for example, and we may see an example later on, if, let's say, these factorized distributions come to be a Gaussian, in essence, in this expectation here, you can think possibly that it may come up that in certain cases, what you do is you may have to fix those z's to their mean values, right? To their mean values. I don't think so. I don't think so. But I know one case that there is a relation between what you see here when you use particle approximations, but in sequential Monte Carlo, this, it's very different. Okay, it's very different. Okay. Now again, remember, so what we did is, right, we took all the latent variables, Q of Z, and we wrote them as a product of factorized, we factorized them one term at a time, Q1 of Z1, Q2 of Z2, etc. So if now distribution Q of Z serves again as a way to, to compute the posteriors of Z, to approximate the posterior of Z given X. So if you think sort of a graph, a directed or even an undirected graph problem, right? You remember in let's say in a directed graph model, if you look, on one random variable in the graph, it only depends on its Markov blanket. You remember what the Markov blanket of one variable is? So basically all the variables that I'm trying to approximate here is like the joint distribution of all the variables on the Markov blanket. So in this case, for example, when you apply this for graphs, this is the summation goes over the Markov blanket and updates one variable at a time, one distribution at a time, keeping the rest basically to where they are. Okay? So this is sort of, you can see how this may be applied to in the context of graphical models. All right. So let's do an approximation of this, okay? A very easy example. There is a lot, these slides contain a lot of details. So they were written by one of my former master's students, okay, who was willing and capable to do all these derivations and provide all the computer programs that go with this lecture, okay? So what he did is he started with a multivariate Gaussian. In this case, we have two variables only, with this mean and covariance looking like that. And he says, you know what? I am going to use this mean field approximation to approximate this Gaussian over two variables as a product of Gaussians over each variable separately. So it's a factorized product of two univariate Gaussians. Okay? You may say, why should I bother to do this? Well, it's interesting, right? I mean, can you actually take, this Gaussian on two variables and write it as a product of Gaussians in one dimension for each of the variables? I mean, that would be interesting, okay? So, and not to mention that actually it's a very good way for you to learn exactly how these variational methods work, right? So let's use the exact formula. The exact formula, you remember it says the optimal Q1, the log of Q1, Z1, so the star means optimal, is the expectation over all the other variables. What other variables are here? Z2 of the log likelihood. There is no hidden variables or anything, there is only Z here. So log of P of Z. So what I'm doing is I'm expanding the log of P of Z for the bivariate Gaussian, all right? Keeping anything that doesn't depend on basically on Z1 out of the picture, okay? Because we're really interested in the distribution of Z1. By the way, with all these constants, whatever result we get, we're going to have to normalize it to be sure that this integrates to 1. So keep that in mind. So you expand this, right? This is a multivariate Gaussian. You expand, and then you have to take expectations with respect to Z2. So every term that has Z2, there is Z2, you're going to have the expectation of Z2 with respect to Z2, okay? There is nothing else. And how do we extract this distribution from this expression? What is the buzzword that we have to do? This is distribution in Z1. I see Z1 here, I see Z1 there, I see Z1 squared. So what do we need to do to come up with a nice expression? What's the buzzword? No, I have the square, and somebody said complete the square. What? No, square, I like the square. I was going to say closing the square or completing the square or, whatever. So you basically have to write this as, Z minus some mean, right, times some matrix times Z minus some mean, all right? So you can get the form of the Gaussian distribution. You have to close the square on Z1, okay? So you can do this in a trivial way. And if you do this in a trivial way, it comes out that the optimal distribution for Z1 is, and again, all the algebra is here, so you don't have to move a finger. The mean comes to be what you see here, okay? And the optimal Q2 by symmetry comes to look like that. So I remind you, mu1 and mu2 are the means, but they're coming from the bivariate Gaussian. And so E of Z2 and E of Z1 are the means of the univariate Gaussians in the factorization, all right? So there is an issue here. You can, not an issue, this is exactly what we discussed about self-consistency. To find Q1 of Z1, you need to know what is the mean of the Q2 of Z2. And to find Q2 of Z2, you need to know what is the mean of Q1 of Z1. So effectively, if you're going to write a little code, you approximate, let's say, this mean, and you compute this, and then you compute its mean mu1, you plug it in here, you calculate this, you calculate a new mean of this, you plug it in, and you iterate until convergence. Okay? It actually comes up that this problem has a really, it's like a fixed point sort of, it leads to a fixed point solution, okay? And so the fixed point solution basically, at the end of the day, gives you these answers that you see here. All right, so when you iterate this, you can do it, but, here is the answer, okay? So the mean of Q1 Z1 is actually mu1, and the precision is lambda 1, and here the precision is lambda 2, and the mean mu2. All right, so let's, I do not have time to check, I'm going to post this, right, but there is Python programs actually that run and get you the pictures that you see here. So I'm going to show you how the results look like. So this is the multivariate Gaussian, the bivariate Gaussian P of Z, and you try to approximate it with this factorized variational distribution Q of Z. All right, so notice, okay, so this is what you get, all right? So this is the product of two univariate Gaussians, and you notice that in the direction of the maximal variance of P of Z, basically you are underestimating, okay? So basically here you're doing good, but you're missing what's going on in there. So this is basically the solution that you get is more compact than the actual P of Z. So basically your Q of Z is over confident approximation of the posterior. Okay. Alternative approximate inverse, we don't need to know this, right? It's basically the same derivation I gave you. I see here when we did the optimization problem, enforcing the constraint that the distribution Qj is normalized. So if you do actually this, you get the right solution right away. So there's nothing new really on this thing. I don't know actually why this came out of sequence. Okay, it doesn't matter. So let me continue this approximation of the Gaussian thing. This is what we said we're getting, okay? So we mentioned that maximizing the lower bound, right, is the same as minimizing the Kullback-Leibler distance between Q and P. So just to make things interesting, what we do here is, how about instead of minimizing this QL between Q and P that comes directly from these variational principles, if we try to minimize instead the distance between P and Q. All right, and remember the Kullback-Leibler distance is not symmetric, so you don't anticipate that this will give you the same results as this. So this is the variational approximation. This is what we're discussing in these few lectures. This is not a variational approximation. We minimize the KL distance between P and Q. All right, big difference. So this is what you get. So can you look at so the Q is all over the space. This is P of Z. So P of Z is 0 there, all right? So Q of Z, you can see when you minimize the distance between P and Q, it puts probability mass where the actual values of P of Z are very small, okay? So before we had an overconfident solution that underestimates the variance in this direction. Here we have a solution that has very high support and non-zero mass in areas where P of Z is equal to 0. So again, be sure if you write any little programs for minimizing KL distances, use this to be concerned how big differences you get when you minimize Q and Q, the distance of Q from P versus the distance of P from Q. And you can actually sort of see how you can expect many of these results, right? So if you look at let's do one of these cases just for demonstration. So in this case, we minimize the distance between Q and P, and this is what this distance is, right? So let's consider regions of the actual distribution that P of Z given X is 0, all right? So log of 0 is how much? What is log of 0? It's big, okay, very big. It's bigly. Who said bigly, actually? I don't remember. Our first-class leader most probably. So this is bigly, okay? So if P of Z given X is big, okay, you get basically, you get an infinite contribution, assuming what? That Q of Z is not 0. All right, assuming that Q of Z is not 0. So what does that mean? That in regions where, you remember, you try to minimize this distance. All right? And if Q of Z is positive when this is 0, you will get a huge number here. So in regions that P of Z is 0, Q of Z has to be what? Look at this expression, right, and consider in regions where P of Z is 0, all right, to avoid getting log of 0, what is the only option that will lead to a minimal of the distance of Q and P? If this is 0, the only way that you get not infinite is when? When Q of 0 becomes 0. And this is what's called zero enforcing for Q of Z. And you can see it here. P of Z is 0, all right? And Q of Z is forced to go to 0. Okay? In this case, and the discussion is on the next slide that you can read, you basically get the opposite. Effectively what you get in regions where P of Z is 0, Q has positive mass, basically. Okay? Quite the opposite effect. What happens if the actual distribution is a Gaussian, right? And you do this mean field approximation, right? That's sort of an interesting problem. So this is let me see what is the actual distribution. So the blue here that you see is the mixture of two Gaussians, and we try to compute a factorized approximation of the two Gaussians, a factorized product of basically of univariate Gaussians, okay? So what you see here, I'm starting with from the minimization of the KL distance between P and Q. Again, I remind you, this is not variational methods, okay? I'm doing this extra, okay? This is not variational methods. It's not maximizing the lower bound. But so this is how the approximation looks. You get basically the red approximation here is univariate, is the product of this, you get basically this Gaussian that you see here, okay? It basically contains the support of the two modes in the Gaussian mixture. If you go, however, and you approximate, you do the variational method, and you approximate you minimize the KL distance between Q and P, you will get either this or either that. So basically, the variational method, what it does is it collapses to one of the modes of the Gaussian mixture. Okay? So this is your standard mode collapse problem. And of course, what does it mean it collapses? I mean, is this algorithm, how is it possible to give you two solutions? Well, you start with something about your mean and variance in the univariate Gaussians. So for some initial guess, it will converge there. For something else, it will converge there. Now, if you do this algorithm, you run it with multiple times with different initial guesses, you can immediately see, let's say 50% of the time you may get this, and 50% of the time you may get that. But keep in mind, so this is the, minimizing the distance between P and Q. This corresponds to the minimization of Q and P, which is our variational techniques discussed today, okay? If we have time, maybe in a week or two, we will discuss basically a whole new set of methodologies, including expectation propagation, basically that lead to this type of approximations that we see up here. But the variational methods, they have this problem with mode collapse. Okay. Can you generalize this problem with, well, there's a lot of things I can be asking here, but, in this slide, basically, and I'm not going to go through it because it's elementary, if somebody gives you an arbitrary distribution P of X in high dimensions and says, find, using variational methods, a Gaussian approximation. Remember we did the simple example to demonstrate the difference from the Laplace approximation, but you may wonder, is there any actual generalization of this to a multivariate distribution? Can I get the variation approximation that's Gaussian? And it comes up actually if you do the algebra, and I have everything here, and I know you are not going to bother to look at it, but somebody bothered to type it, so out of respect for him, you may want to actually read it, all right? Because there is very much to learn. There is a little trick that you do. It's a standard trick in machine learning with this term here. I am not going to discuss it. Since you need to take derivatives with respect to mu and sigma to find the optimal Q of X, you need to know how to do these derivatives. But here is the answer. The answer comes to be that the mean in the variation approximation is actually the expectation of X, and the variance is actually the covariance of X. Okay? So sigma is exactly the covariance of X. So really, there's no factorization here, right? So this is a multivariate Gaussian. Okay? So if you want to do this, you can use variational methods. This is not the result is very much different from the Laplace approximation. Okay? Very much different. Can you generalize this method to sort of different type of distributions? Because KL distance, lots of people criticize it. I remember, once upon a time I gave a seminar in a British university, and one of my colleagues says, this is very bad and not a good distance. And since then he wrote 25 papers using the KL distance for some trivial 1D problems. Hopefully, and so lots of people, including ourselves, right, we use the KL distance because it's convenient. We know, everybody knows the deficiencies, okay? But it's all about, mathematical simplicity and knowing exactly when things work and when things don't work, okay? So you can generalize this KL distance to what's called the alpha family of divergence, okay? And this is the definition of this distance with parameter alpha, all right? It looks very much different from the KL distance, okay? So this parameter alpha is from -∞ to infinity, and it is obviously greater or equal to 0. It's equal to 0 when P and Q are equal. If you want to actually read everything about calculations with this type of alpha distances, Milka has a very nice report, okay, that you can download from Microsoft website with all the derivations actually in the appendices, so you can see lots of very interesting type of extensions of the KL distance. So let me see if I need to tell you anything here. So basically, what I have in the next two slides is to show you some limited values of these alpha distances when alpha takes values close to 1, basically, to see what exactly you're getting. And so if you define this coefficient 1 plus alpha over 2 as gamma p, and this coefficient as gamma q, or is the exponent of the Q distribution, obviously gamma p and gamma q equal to 1. So if you take the limit of these gammas when alpha goes to 1, you can see this goes to 0, this goes to 1, and what you can do is actually you can take these powers in the definition of these alpha distances and use first order Taylor expansions. The results are actually trivial, so I'm not going to go through everything here, okay? So for example, if you take the distribution q to gamma q, you can write this as the exponential of gamma q log of q, and then you can use a first order Taylor series expansion in gamma q, because gamma q goes to 0 as alpha goes to 1, so you can write this as exponential is 1 plus x squared over 2. So the first term is 1 plus gamma log of q. This is a little bit more tricky, but it's nothing major. You can approximate as p minus gamma qp of log of p. And it comes out that this integral, it gives you a very nice form that maybe some of you have seen it in different contexts in machine learning. So if you take these asymptotic values and you plug them in there, you get basically, you recover from these alpha distances the KL distance, okay? So as a matter of fact, when alpha, we said alpha goes to 1, right? When alpha goes to 1, this becomes equal to 1, so you get the KL distance, okay? And so these have some limiting values, okay? So when alpha goes to 1, you get the KL distance. And actually here, yeah, so this is correct. And you can get the reverse KL distance when alpha goes to -1. And even further, you can get out of this even the Henninger distance that some people in network theory use, right? So this is recovered by taking alpha equal to 0. Okay. Let me see if I am going to tell you about this. All right, so let's, let me see how we're going to define this problem. So in everything we did, like when we apply expectation maximization, right? You remember we had a set of latent variables z, but also we had a set of parameters, okay? And in the expectation step, what we did is we computed the efficient statistics that they were effectively expectations with respect to the z variable for fixed parameters, and then once we computed the sufficient statistics, then we maximize a lower bound, literally, right? It was the joint log likelihood with respect to the parameters theta, all right? So the idea is here, can I do a variational approximation, or what is that going to give me, where the joint distribution of the unknown latent variable z and the parameters theta factorizes as what you see here. Actually, I put here q of zeta comma theta, all right? Now, if you want to keep the parameters theta to a fixed value, all right, and you don't want to bother, basically this q of theta becomes a delta function, okay? And so let's see what case this is considered here. So the maximization of the lower bound is the same as the minimization of the distance between q and p. So the distance between q and p is written minus q of theta, q of z. This is the factorization I used. This is the joint log likelihood, q of z, q of theta, just the definition, okay? If we start with the parameters fixed, what part of the EM algorithm that reminds you? So in other words, if I say, let's fix the parameters to the value theta 0, that would be the expectation step, all right? So let's see actually, does the expectation step has anything to do with variational methods, right? So we're going to keep theta fixed to values theta 0. So, let's see what we get. Look on the calculation that involves basically the numerator there, all right? Q of theta is a delta function, so you agree that I'm going to get there log of z of p of z comma theta 0, all right? The rest basically, with theta we don't really care because I am looking now on z to update z. So I have minus q of z log of p z theta 0, so minus q of z, okay? So I'm taking the, here is the join log likelihood. This is what we use in expectation maximization. And I write this as the posterior of z given the parameters times the probability of theta 0, the posterior of theta 0 basically. Okay, so this doesn't matter for z, so I get rid of it, so minus q of z, log of this divided by qz, okay? And when is the minimization? So we need to minimize this KL distance, all right? All right? So when is the minimization happening? When q of z equal to p of z given theta 0 comma x. This is what actually we did on the expectation step, right? We fixed the parameters, all right? And you remember what we did is we computed the average of the joint log likelihood with respect to what distribution? What was the distribution in the step that we averaged with? It was the posterior of z given the parameters. Well, here when we do variational methods, it comes that the optimal q of z, it is the posterior of z given theta 0. So the step actually does come from, it's a small part of the variational methods. Okay? Then you may ask about the maximization step. Well, so we have updated now q of z equal to that, and we want to compute q of theta. So we go back to, again, to the lower bound. Okay, so you remember it is q of theta, q of z. the joint log likelihood of everything, data and unknowns, okay? And in this case, remember the z is fixed now, okay? So I put q of z inside, and what I get is, this term times that, is the expectation with respect to q of zeta of the joint log likelihood, all right, okay? And I have then I have an average with respect to q theta, and then on the denominator, basically I'm going to get the entropy of the distribution theta. And how do you update q of theta? You basically need to maximize, look at this, right? How are you going to maximize this? You're going to find the theta 0 that maximizes the joint log likelihood. And actually, yeah, that's, I was thinking here, just having a generic theta rather than theta 0, but I suppose we update theta 0 here. So this is the M step, all right? You already have computed the sufficient statistics with respect to the distribution Q of Z that we computed, and then you maximize the joint log likelihood with respect to the parameters. Bottom line is, when you apply this variational method for a distribution that factorizes the latent variables and the parameters like that, basically you discover, as you update Z first and then you update theta, you discover the E and M steps of the expectation maximization algorithm. As a matter of fact, the EM algorithm, if I remember historically, was developed way before people in machine learning started using the variational methods, but now you can see sort of the EM algorithm is really a variational approximation, okay? Nothing special. All right, 138, I only have time to actually do one example, then we'll come back to these slides because they have a lot of substance, okay? You guys have maybe, some of you have not seen this example, but we did this, and I think we gave you, did we give them a homework on this semester? All right, so you all have seen it, okay? So this is the denoising of an image problem, where you can think of this being the pixels in an image. These are the noisy values, and X are the, the original image, but here we take it to be a binary, black or white, okay? +1 or -1, okay? So the joint distributions of X and Y is P of X times the likelihood of P of Y given X, okay? So I am going to do some manipulation of the algebra, okay? Just to make things, to generalize things. So the first thing I'm going to assume a prior, so we want to compute X, right? We want to compute what the original image is if we have some noisy version of the image. That's what denoising is. So the prior on X I'm going to assume it will have, it will be an exponential family distribution, will be e to the minus some energy, and this energy functional, I write it like that, where I account only for interactions between neighbors. So this is sort of a generalized Ising model, okay? So I put some weights between pixels I and j, but I only account for these interactions I and j if I and j's are neighbors, okay? So this is my, this is a very standard way, to introduce basically the dependencies between the X pixels, okay? So again, there is a reason I'm writing this as e to the minus e, like a Gibbs distribution, and this is my energy. And let's see what the likelihood is going to be like. So the likelihood is a product of terms for each I, right? So it is the probability of yi given xi, so you can think of this sort of being a Gaussian with some described noise. So what I'm going to do is I'm going to write each of these terms to follow this format as e to some energy li, right? So because it's product of exponentials, then I'm going to get the expectation of the summation of all the li's. And these LIs can be Gaussians, right, with some noise there. Okay? All right? Easy. So if I compute the joint, or, you know, if you forget the normalization or the posterior of x given y, I get e to the minus the energy E, where the energy is E0 minus the summation of all the LIs. Okay? So my energy in my joint log likelihood, this is what we need for the variational methods, is e to the minus this energy. Okay? All right. So this is the exact model. All right? So we want a variational approximation now, because this looks complicated. I mean, the only way you can actually play with this is with sampling methods, with Monte Carlo. Okay? And so what we want to do is, we want to approximate this with a factorized product of QIs, and you remember xi is a binary variable, +1, -1. So really the only parameter in this binary distribution QI is the mean μi. That's why I'm writing that explicitly there. So really, if I compute for each of these distribution μi, I'm done, because that will define the distribution QI. All right. So let me. So you remember what is the result from the mean field approximation is that. So this is, you know, we have an update for each factor. All right. Given the average of the joint log likelihood in the average field over all the other factors. Okay. And so here I'm going to do the following thing to simplify this calculation, because it's an exponential. I am going to define so I did not put the y here, right? But this is sort of, you can think of this as the joint log likelihood. Right? This is what it is, okay? So the joint log likelihood is, the joint log likelihood will make this exponential to disappear, and it will be, there's a minus sign there, so it will be xi times the summation over the neighbors of wij xj, all right, plus li of xi, plus constants. So what I have done here is, I am writing the joint log likelihood, but because I'm interested to only calculate one factor at a time, I am only looking at the terms that contain xi, nothing else. So there is many other terms, right? There is x1 here times all the neighbors, and x2. You only want to see xi because effectively this is what I'm interested to compute in some iterative manner. So the joint log likelihood is this, okay? So, all right, nice. So we already know what the optimal distribution is. We know that the log of the optimal QI is, you remember, it is the expectation with respect to all the Qs, and here is that, all right? So the QI is the expectation, okay, of xi times this, where I substitute xj with mu j. What is that? Because QI is the expectation of, I'm sorry, QI is the exponential of the expectation of this. And what is the expectation of xj because it's a binary variable? It's mean. So effectively, in this trivial model, you calculate QI by fixing all the other x's to their average value. Very nice. All right, so that's, you know, it's an extremely easy calculation. So you don't really have to calculate any sufficient statistics, any complicated expectations. You just fix xj with the mean, all right, because you need to take expectations, okay? And I want you to read the rest, right? But effectively, we're calling this term here mu I, okay? And we define the values of Li, Li plus and Li minus. Okay, I'm going to finish, right? So I'm going to come back to this example. So we basically, at the end of the day, you can derive the mu I to have a very nice closed solution. Okay, closed solution. So if you write an algorithm, it would be one line, and if you apply the mean field approximation in a self-consistent manner to images, you can see, with one